Well, welcome back to our course on networks and distributed systems. Based on the textbook Computer Networking, a Top-Down Approach by Jim Couros and Keith Ross. We are in Module 5 at this point, which is a study of the link layer of the TCP/IP model. In the last lesson, we started the discussion of Ethernet. Let's pick up where we left off. We've been talking about Ethernet as if it were a single protocol standard. The fact is, though, there are a number of different Ethernet versions, such as 10 base T, 10 base 2, 100 base T, and more. Other Ethernet technologies have been standardized over the years by the IEEE 802.3 CSMA/CD working group. The first part of the acronym refers to the speed of the standard. 10 megabits per second, 100 megabits, gigabit, and 10 gigabit Ethernet, respectively. Base refers to baseband Ethernet, meaning that the physical media only carries Ethernet traffic. Almost all of the 802.3 standards are for baseband Ethernet. The final part of the acronym refers to the physical media itself. Ethernet is both a link layer and a physical layer specification, and is carried over a variety of physical media, including coaxial cable, copper wire, and fiber. Generally, the T refers to twisted pair copper wires. Historically, an Ethernet was initially conceived of as a segment of coaxial cable. The early 10 base 2 and 10 base 5 standards specify 10 megabits per second Ethernet over two types of coaxial cable, each limited in length to 500 meters. At the time, the token ring technology specified 16 megabits per second, for example. Longer runs could be obtained by using a repeater, a physical layer device that receives a signal on the input side and regenerates the signal on the output side. You recall in an earlier lesson that I mentioned that a hub was in fact a multi-port repeater or amplifier, and that would make a hub a physical layer device because it does not do any direction of the frames. It simply takes a frame in one port and sends it out every other port that it has. A coaxial cable, as seen in figure 5.20.4, corresponds to the view of Ethernet as a broadcast medium. That is, all frames transmitted by one interface are received at all the other interfaces in a bus topology. Now, a bus topology is a topology where all of the devices are connected to the same bus or cable. Ethernet's carrier sensing multiple access collision detection protocol solves the problem of the multiple access caused by that arrangement. Nodes simply attach to the cable and we have a local area network. Ethernet has passed through a series of evolutionary steps over the years, and today Ethernet is very different from the original bus topology designs using coaxial cable. In most installations today, nodes are connected to a link layer switch, not a physical layer hub. They are connected via point-to-point segments made of twisted pair copper wires or fiber optic cables, which means that only two devices are competing for the link, the host and the switch. Now this simplifies the multiple access problem a lot. In the mid-1990s, Ethernet was standardized at 100 megabits per second, 10 times faster than 10 megabit per second Ethernet and faster than the 16 megabit per second token ring. The original Ethernet MAC protocol and frame format were preserved, but higher speed physical layers were defined for copper wire, 100 base T, and for fiber, several versions, 100 base FX, 100 base SX, and 100 base BX. Figure 5.21 shows these different standards and the common Ethernet MAC protocol and frame format. Make a special note of this information. 100 megabit per second Ethernet is limited to a 100-meter distance over twisted pair and several kilometers over fiber. This specification over fiber allows Ethernet switches in different buildings to be connected. Gigabit Ethernet is an extension to the highly successful 10 megabit per second and 100 megabit per second Ethernet standards, offering a raw data range of 1,000 megabits per second. Gigabit Ethernet maintains full compatibility with a huge installed base of Ethernet equipment. The standard Gigabit Ethernet, referred to as IEEE 802.3z, does the following. First, it uses the standard Ethernet frame format and is backward compatible with 10 base T and 100 base T technologies. This allows for easy integration of Gigabit Ethernet with the existing installed base of Ethernet equipment. 2, it allows for point-to-point links as well as shared broadcast channels. Point-to-point links use switches while broadcast links use hubs as described earlier. In Gigabit Ethernet jargon, hubs are called buffered distributors. Third, it uses carrier sensing multiple access collision detection for shared broadcast channels. In order to have an acceptable efficiency, the maximum distance between nodes must be severely restricted. It also allows for full duplex operation at 1 gigabit or 1,000 megabits per second in both directions for point-to-point channels. Initially operating over optical fiber, Gigabit Ethernet is now able to run over Category 5 UTP cabling, that's twisted pair. 10 gigabit per second Ethernet, 100 G base T, was standardized in 2007, providing yet higher Ethernet LAN capabilities. In the days when bus topologies and hub-based star topologies were used, Ethernet was clearly a broadcast link in which frame collisions occurred when nodes transmitted at the same time. Don't forget that unlike a link layer switch, a hub is little more than that multi-port amplifier. To deal with these collisions, the Ethernet standard included the carrier sensing multiple access collision detection protocol, which is particularly effective for wired broadcast LAN spanning a small geographical region. But if the prevalent use of Ethernet today is a switch-based star topology using store and forward packet switching, is there really a need for an Ethernet MAC protocol? A switch coordinates its transmissions and never forwards more than one frame onto the same interface at any time. Furthermore, modern switches are full duplex so that a switch and a node can send frames to each other at the same time without interference. In other words, in a switch-based Ethernet LAN, there are no collisions and therefore there is no need for a MAC protocol. By the way, as a side note here, if you had a node that had an Ethernet adapter that could function at 10 megabits per second, connected to a port on an Ethernet switch, a link layer switch that could send data at 1 gigabit per second, how fast could the two devices transmit data over the link? How about 10 megabits per second? You can't go any faster than the slowest device. Let's move on. Why don't we take a few minutes to talk about how link layer switches work. The role of the switch is to receive incoming link layer frames and forward them to outgoing links. The switch itself is transparent to the host and routers in the subnet. That is, a host or router addresses a frame to another host or router rather than addressing the frame to the switch. It sends the frame into the LAN unaware that a switch will be receiving the frame and forwarding it on. The rate at which the frames arrive at any one of the switch output interfaces may temporarily exceed the link capacity of that interface. To accommodate this problem, switch output interfaces have buffers in much the same way that router output interfaces have buffers for datagrams. Filtering is the switch function that determines whether a frame should be forwarded to some interface or should just be dropped. Forwarding is the switch function that determines the interfaces to which a frame should be directed and then moves the frame to those interfaces. Switch filtering and forwarding are done with a switch table. A switch table contains entries for some, but not necessarily all, of the hosts and routers on the LAN. An entry in the switch table contains a MAC address, the switch interface that leads to that MAC address, and the time at which the entry was placed into the table. Although this description of frame forwarding may sound like our discussion of datagram forwarding in the module on the network layer, there are differences. One important difference is that the switch forwards packets on MAC addresses rather than IP addresses. A switch table is constructed in a different manner from a router's forwarding table. To understand how switch filtering and forwarding work, suppose a frame with a destination address DD, 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 and no, we don't have a skip in the video, arrives at the switch on the interface X. Notice that the switches are using a hexadecimal MAC address and not an IP address. The switch indexes its table with the MAC address dd.dd-dd-dd-dd-dd, and there are three possible cases. 1. There is no entry in the table for dd-dd-dd-dd-dd. In this case, the switch forward copies of the frame to the output buffers preceding all interfaces except for interface X, since it came in on interface X. In other words, if there is no entry for the destination address, the switch broadcasts the frame, much like a hub. The second option could be that there is an entry in the table associating dd-dd-dd-dd-dd with interface X. In this case, the frame is coming from a LAN segment that contains the adapter dd-dd-dd-dd-dd. There being no need to forward the frame to any other interfaces, the switch performs the filtering function by discarding the frame. In other words, if the switch has the frame listed as going to interface X and that frame arrives on interface X, it knows not to send it back. Third option is there is an entry in the table associating dd-dd-dd-dd-dd-dd with interface Y. In this case, the frame needs to be forwarded to the LAN segment attached to interface Y. The switch performs its forwarding function by putting the frame in an output buffer that precedes interface Y. Suppose that a frame with a destination address 62-FE-F7-11-89-A3 arrives at a switch from interface 1. The switch examines its table and sees that the destination is on the LAN segment connected to interface 1. This means that the frame has already been broadcast on the LAN segment that contains the destination. The switch therefore discards the frame. Now suppose a frame with the same destination address arrives from interface 2. The switch again examines its table and sees that the destination is in the direction of interface 1. It therefore forwards the frame to the output buffer preceding interface 1. It should be clear from this example that if the switch table is complete and accurate, the switch forwards frames towards destination without any broadcasting. Let's take a break right here, and we will pick up after you've had an opportunity to review your notes and update your study guide.